Space has always been the frontier of scale, a place where our minds strain to comprehend distances, masses, and energies far beyond everyday experience. Yet in early 2025, astronomers revealed something that stretches these limits even further. They discovered what appears to be the largest coherent structure in the nearby universe, a superstructure so vast and massive that it challenges how we map cosmic architecture. Its name is Quipu. Quipu, named after the ancient Incan knotted measuring system, is not just another supercluster. It's a filamentary behemoth composed of galaxy clusters and superclusters. Knots and cords across space, stretching over 1.3 to 1.4 billion light-years in length. That alone makes it larger than many previously known cosmic structures. But the awe comes not only from its size, it's what Quipu tells us about how the universe is built, how matter is distributed, and how our cosmological measurements might have hidden complications. Let's walk through 10 insights about Quipu, 10 reasons this discovery matters deeply to cosmology, astrophysics, and our understanding of the universe. First, scale and mass. Quipu spans more than 400 megaparsecs. In astronomical terms, that's over 1.3 billion light-years. Its mass is equally staggering, about 2x 1017 solar masses. Put simply, Quipu holds the equivalent of about 200 quadrillion suns. That makes it not just one of the largest by size, but among the most massive known cosmic structures. Second, the discovery was enabled through X-ray galaxy cluster surveys. Specifically, researchers used data from the ROSAT satellite via the Classic survey. Galaxy clusters emit strongly in X-rays because of hot intracluster gas. Mapping those bright X-ray signals allows astronomers to identify where dense matter, both visible and dark, clusters together. That's how they traced the knots in the cosmic web that define Quipu. Third, Quipu is part of a set of 5 superstructures discovered in that survey. Along with Quipu, the Shapley superstructure, Serpens, Corona Borealis, Hercules, and Sculptor Pegasus were identified. Together, these 5 account for about 45% of the galaxy clusters, 30% of galaxies, and 25% of matter in the region surveyed, while occupying just 13% of the volume. That tells us the universe is very lumpy. Much of its matter is concentrated in relatively small, filament-rich regions. Fourth, the filamentary shape. Quipu isn't a blob. It resembles a long spine with side filaments, like a cord with smaller strands branching off, reminiscent of the knotted cords of a Quipu device. This shape reflects how cosmic matter tends to organize, into the cosmic web, with filaments connecting dense nodes, clusters, and vast voids in between. That morphology shapes how galaxies evolve and how gravitational effects propagate. Fifth, implications for cosmological measurements like the Hubble constant and the cosmic microwave background, CMB. Because Quipu is so massive and nearby in cosmic terms, its gravitational pull can induce streaming motions in galaxy clusters. These motions can subtly affect redshift-based measures of expansion rate, the Hubble constant. Also, large superstructures can produce distortions in the CMB through mechanisms like the integrated Sachs-Wolf effect, the way photons gain or lose energy when crossing large gravitational wells. Observations suggest that Quipu might already be leaving such signatures. Sixth, it helps test cosmological models, especially the standard LCDM, lambda cold dark matter model. The existence of Quipu shows that simulations under LCDM can produce structures of similar size and mass, but observing them helps calibrate and constrain the model, especially how clustering, dark matter and dark energy interplay on large scales. If structures like Quipu were impossible under LCDM, it would signal a need for revision. So far, Quipu is consistent with simulations, but it pushes the limits. Seventh, the environmental effect on galaxy evolution. Galaxies inside or near superstructures like Quipu experience different gravitational and gas dynamical environments than isolated galaxies. There tends to be more interactions, hotter intercluster medium, and stronger tidal forces. These can accelerate star formation but also accelerate quenching when galaxies stop forming stars. Studying galaxies in Quipu versus more isolated field galaxies can reveal how the cosmic structure influences galaxy life cycles. Eighth, Quipu's detection leverages our improved ability to survey large parts of the sky. The Classic survey covered about 86% of the sky, excluding only areas obstructed by the Milky Way, known as the zone of avoidance. Even with these blind spots, Quipu shows up strongly in both cluster and galaxy distribution maps. This reflects progress in data collection, sky coverage, and statistical methods that let us find structures that might previously have been invisible or ambiguous. Ninth, Quipu is located in the nearby universe, meaning it is relatively close in cosmic terms, about 425 to 800 million light-years away, or redshift roughly 0.03 to 0.06. This proximity means we can study it in detail, its galaxy clusters, cluster gas, lensing effects, and mapping its matter distribution more accurately than extremely distant or ancient structures. That closeness makes it especially important for refining our understanding of how large-scale structure behaves today. 10th, Quipu's discovery is both humbling and inspiring. Humans once believed in great walls or walls of galaxies. We knew about Laniakea, the Sloan Great Wall, Hercules' Corona Borealis Great Wall, but many of those are uncertain or at limits of detection. Quipu is currently the best characterized, most reliably measured structure of its size in the near universe. It reshapes our cosmic perspective, reminding us that what we observe is only a subset of what may be out there. Larger structures may exist deep in the universe beyond our observation horizon. Quipu is a milestone, not a finish line. These insights pull us deeper into how extraordinary Quipu is, and why its discovery matters now, not just as trivia, but as a lens through which many existing puzzles in cosmology sharpen or shift. Imagine what it must be like, standing on a cluster of galaxies that lies within Quipu. You look up, not just at your own galaxy but across strings of clusters stretching billions of light-years like beads on a giant knotted ribbon. Invisible dark matter giving shape, hot gas glowing in X-rays, gravity pulling, light bending. Through your observatory you see the sky subtly distorted by lensing and in readings of cosmic background radiation, faint but real imprints of this massive structure. Further, consider what future telescopes and surveys might see. More precise mapping of dark matter, more detailed X-ray and radio wave observations of the intercluster medium, refined measurements of Hubble tension. That odd discrepancy in our measurements of how fast the universe expands could be resolved or complicated by Quipu. By studying Quipu, researchers can tighten error bars in cosmological constants, better model how matter clusters on large scales, understand how dark energy acts in the presence of such giant structures, and perhaps gain more clarity on early universe conditions. The cosmos, it seems, is more intertwined than ever imagined. Quipu reminds us our universe is not just peppered with galaxies, but laced with gigantic cosmic threads, structures so vast they shape what we see, how fast galaxies move, even how we interpret the afterglow of the Big Bang. Here at Beyond Binary, we believe science isn't just about knowing. It's about letting those discoveries reset the way we understand our place in the cosmic web. So the next time someone asks how big can get in the universe, tell them about Quipu, the largest known superstructure we've reliably mapped right now, and get ready, because the universe may still have more knots. If you found this journey through Quipu fascinating, please like, share, and subscribe. Drop your thoughts in the comments. What implications of Quipu intrigue you most? Do you think larger structures wait to be discovered? Until next time, keep your curiosity cosmic and your questions beyond binary.